This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. We're diving into the fascinating world of supermassive black holes today. We're exploring how these cosmic behemoths grow within densely packed star clusters. It's a story of galactic mergers, gravitational waves, and some seriously mind-bending physics.
And it all starts with seeds, incredibly small seeds that somehow blossom into these giants. It's like watching a tiny acorn grow into a redwood, only on a cosmic scale.
Exactly. These seeds, sometimes just stellar mass black holes, undergo a process of runaway growth fueled by mergers and gas accretion. It's a bit like a cosmic snowball effect, you know?
And the James Webb Space Telescope is giving us an unprecedented view of this process at high redshifts, revealing a population of distant SMBHs that were previously hidden. Amazing, right?
It's truly revolutionary. We're talking about observing black holes forming and growing just a few 100 million years after the Big Bang. That's incredibly fast. Wow. Let's talk about these seeds. How do these relatively small black holes get started in the first place?
Well, there are a few theories. One involves runaway stellar collisions within dense nuclear star clusters. Imagine a cosmic game of billiards, but with stars and black holes.
A cosmic game of cool. I like that. So these collisions create even more massive stars, which then collapse into larger black holes.
Precisely. And then these larger black holes can continue to grow through gas accretion, essentially gobbling up surrounding gas at an incredible rate.
And what about mergers? Do black holes collide and merge with each other?
Absolutely. Binary black holes form, and their gravitational dance eventually leads to a merger, creating an even more massive black hole. This is a key part of the growth process.
So it's a combination of collisions, accretion, and mergers all working together to build these supermassive black holes. It's a complex process, isn't it? The article mentions using simulations and semi-analytic models to study this. How do these tools help us understand this complex process?
Simulations allow us to model the three-dimensional evolution of dark matter, gas, stars, and black holes. It's like creating a virtual universe on a computer.
A virtual universe. That's pretty cool. But these simulations can be computationally expensive, right?
Very expensive. That's why semi-analytic methods are also used. They're faster, but they rely on some simplifying assumptions.
So it's a trade-off between accuracy and computational cost, a classic scientific dilemma.
Exactly. Each approach has its strengths and weaknesses, and combining them often gives us the best understanding.
What kind of observational evidence supports this model of SMBH growth?
GWST observations of distant SMBHs are crucial. They show that these massive black holes existed much earlier than previously thought.
So the JWST is providing a crucial piece of the puzzle. Are there other observational clues?
Yes, we can look for intermediate mass black holes, which are thought to be stepping stones on the path to supermassive black holes.
Like a cosmic stepping stone? And what else?
Nuclear star clusters themselves are important. Their mass is correlated with the mass of the central black hole, suggesting a close relationship.
So the star clusters are essentially the nurseries for these supermassive black holes.
You could say that. And we can also look for evidence of gas accretion onto these black holes, as well as gravitational waves emitted during mergers.
Let's talk more about gravitational waves. How do they play a role in this story?
Merging black holes emit gravitational waves, ripples in space-time. Detecting these waves can give us information about the mergers themselves.
So we can essentially listen to the universe and hear these black holes merging?
Exactly. And the rate of these mergers can tell us about the overall rate of SMBH growth.
And what about the stochastic gravitational wave background? Is that relevant here?
Yes. The cumulative effect of many mergers creates a background hum of gravitational waves. Detecting this background can provide further evidence.
It's like the universe's own symphony of gravitational waves.
A cosmic orchestra, if you will.
The article also mentions tidal disruption events. What are those?
These occur when a star gets too close to a black hole and is ripped apart by the intense gravitational forces.
A cosmic spaghettification?
You could say that. These events are quite dramatic and can produce observable electromagnetic signals.
So we can actually see the effects of these tidal disruptions?
Yes, they're a powerful way to probe the properties of black holes.
And how frequent are these events?
The model predicts a high rate of tidal disruption events, much higher than the rate of black hole mergers.
What are some of the challenges in studying SMBH growth?
One challenge is the computational cost of simulations. Modeling these processes accurately requires significant computing power.
And are there any limitations to the models used?
Yes. Semi-analytic models rely on simplifying assumptions, which can affect the accuracy of the results.
What are some of the future directions for research in this area?
More sophisticated simulations, improved observational data, and better theoretical models are all needed.
And what about the role of future gravitational wave detectors?
They will be crucial in detecting more mergers and refining our understanding of SMBH growth. The data from LISA, for example, will be invaluable.
That was a great discussion. Thank you for sharing your insights into this fascinating area of astrophysics. It's clear that the study of supermassive black hole growth is a vibrant and rapidly evolving field.
My pleasure. It's an exciting time to be studying these cosmic giants.
This conversation is brought to you by PhD Lite.